talking about these optimization problems, that word inscribed shows up a lot. And it just means that generally speaking, we're going to try to draw the thing inside of it, but touching it. So for example, here, we know I've limited us to just the first quadrant, and the line y equals 12 minus x would do something like this. We're thinking about all of the rectangles that I can fit in there that are touching both axes. And specifically that phrase inscribed is going to tell me that one corner of the rectangle has to touch that line. So it doesn't matter exactly how we draw it in. I'm just going to pick an arbitrary point and draw it in. So that's the rectangle we're talking about. And we're looking to find the largest rectangle. And when we say largest, sometimes that might mean we're talking about a volume, but in this case, because we have a two-dimensional shape, we're just talking about area. So I'm going to give everybody a few minutes to try this on your own. Couple things. Going into that final exam, it's possible you're going to have word problems that are not going to tell you what kind of problem it is, right? So thinking through sort of the types of word problems we've seen. We've certainly had related rates problems. Now we've got these optimization problems. And then if I'm kind of giving another category of problems, maybe we're thinking about those velocity or rates of change kind of problems, like average rate of change, instantaneous rate of change stuff. So when we read the problem, we kind of need to get in the mindset of what type of problem it is first to know how to proceed. So when I'm reading through this, that word largest is what's telling me, oh, we're doing optimization here, right? I'm looking to make something bigger, smaller, faster, shorter, right? But I'm looking to optimize something. So that word largest is what tells me it's an optimization problem. And then I'm going to start by writing the equation for whatever it is we're trying to optimize. We kind of have to deduce here that the largest rectangle means the largest rectangle by area. So the area of a rectangle, I would just start off in words. So area of a rectangle is base times height. And so on my picture, I'm going to go ahead and label those as X and Y for the base and the height. So I would say my area is equal to X times Y. And then I'd go, oh, darn, I have too many variables. I sure hope I know something else. Well, the something else that we know is that because that corner touches the line, we know what Y equals. Because the corner touches the line, I know that Y is equal to 12 minus X. Now we get to do the calculus thing, which is we need to take a derivative and set it equal to 0, because that's how we find a max or a min. Personally, I would choose to not do product rule. Personally, I would choose to multiply that out to say 12x minus x squared, so that my derivative becomes 12 minus 2x. And when I set that equal to 0, I get that x is equal to 6. Now, if I wrote this problem, which I did, I would expect you to demonstrate that that really is a maximum and not a minimum. I would say that's usually more easily done by the second derivative test than the first derivative test on these optimization problems. So I would go ahead and take that second derivative and get -2, which means that it's concave down, which means that really was the max. And then I go back to make sure that I'm answering the question that was asked. And the question says to find the dimensions. So if I'm going to find the dimensions, I know that x is equal to 6, but I need to plug that back in to get the y value as well. When I plug that back in, 12 minus 6 is also 6. So my final answer would be a 6 by 6. I'm going to pause in case there are questions. And then my plan is to do a bunch more optimization, but I can do other things too. You'll just have to let me know if there's something other than optimization you want to do today. Yeah, questions. I like questions. Sure. And the square is also a rectangle. Yep. Not all rectangles are squares, but all squares are rectangles. Yep. Yeah, so if we talk about that, and oftentimes we call it the functional domain because it's like what makes sense in the context. So if we look for the functional domain here, I don't have a rectangle if my width or my base shrinks down to 0. And if my base goes all the way up here, I didn't label this on the graph, but that's 12 and that's 12. So if X gets all the way up to 12, then my height is 0. So I would say that in terms of like the functional domain for this thing, X is constrained between 0 and 12. Yeah. I can't have like a negative value for X, both because I said we're stuck in the first quadrant, but also because I can't have like a negative length of a side. Yeah. Oh, and there's a question about how I got that Y was equal to 6. So once you get the value for one of the variables, we'd stick it into the equation to get the other one. So if X is 6, that means Y is equal to 12 minus 6 or 6 also. This one was intentionally not super messy. Okay, so there's a question about the domain and whether these should be closed brackets or open brackets. Personally, I don't think that an area of 0 counts as a rectangle. So if you're asking for my personal opinion, I am not closing those brackets because I don't agree that we have a rectangle if the area is 0. We are trying to fit a cylinder inside of a cone. And if you draw really well in 3D, more power to you. I do not. So I'm going to draw in 2 dimensions and you all can imagine that it's in 3 dimensions. So we've got a cone. I don't know why, but when I think about a cone, I think about it with the tip down and the circle part at the top. But it doesn't really matter. How do you think about your cone? Circle part at the bottom, tip at the top? Let's do that. Okay. So here's our cone. It's got a height of 6 and a radius of 2. So like the height is 6 and the radius is 2. There's my cone. And then we're putting a cylinder inside of that. So a cylinder I can kind of manage to draw in 3D a little bit. So we're like putting a cylinder inside of that, side of that cone. Isn't it lovely? You can imagine how well I draw. So now comes the fun part. Well, we're looking for the dimensions of the largest cylinder. In this case, because they're both 3-dimensional shapes, that word largest should lead us to be thinking volume, not area this time. So the volume of a cylinder is pi r squared h. And then I look at that and I go, oh darn, I've got too many variables. I sure hope we know something else. And in order to know something else, I'm going to take this picture as it's drawn and kind of simplify it down a little bit. I'm just going to look at half of it. And on that half, our cone had a radius of 2. I don't know why I wrote it as an R up there. We know that it's 2. And a height of 6. This R and this H correspond to that cylinder that we stuck inside. So that R and that H for the cylinder that we stuck inside. So the way that I'm going to know something else about that R and H to get rid of a variable is to think about similar triangles in some way. There are 3 similar triangles in there. There's the big one, the little one at the top, and the little one on the right. And it doesn't actually matter which 2 we compare, but we're going to have to compare 2 of those. So I'm just going to talk out loud for a second. In this equation, I'd probably rather replace the H than the R squared, because I'd probably prefer to not have to square something. So whatever happens down here, I'm going to want to rearrange it to make it say H equals anyway. And because of that, I'm going to choose probably the smaller triangle in the right-hand corner that has an H. So if I look at the big triangle, that's got a height of 6 and a radius of 2. And if I look at this smaller one from the corner, it has a height of H. And this, I don't know why I keep saying 2 and writing R. Like I've done that 3 times now. It's a 2. So this side right here, it's this piece, meaning it's 2 minus the R. So this side is 2 minus R. So I think about this as if these are the angles that they share, then tangent theta for this triangle is 2 over 6, and tangent theta for this triangle is 2 minus R over H. And then you can cross multiply as long as you do the right thing. Otherwise, you can multiply both sides by 6H to end up at 2H is equal to 6 times 2 minus R, or H is equal to 3 times 2 minus R. Or H is equal to 6 minus 3R. I think I got all that right. So now I have something to come back up here to replace H with. So my volume as a function of just the radius would look like pi times R squared times 6 minus 3R. And now you know what to do. Take a derivative, set it equal to 0. Or if you want, do a little bit of algebra first so that you don't end up with a product rule. I'm going to multiply things out before I take a derivative and say that our V is equal to 6 pi R squared minus 3 pi R cubed. So when I take that derivative, that's 12 pi R minus 9 pi R squared, which means I can factor out a pi, and I can factor out an R, and I can factor out a 3. And if I pull the 3, the pi, and the R out from this first piece, I'm just left with a 4. And from the second piece, I'm left with 3R. So I'm getting values of r equals 0 or r equals 4/3. Personally, I'm going to say I do not have a cylinder if the radius is 0. So thinking back to that domain piece, I would say that our domain is that the radius has to be bigger than 4, but smaller than 2. Because if we get out to 2, the height is going to have to be 0 if it's going to stay inside the cone. And yes, you could argue that we should include those endpoints. I just say we don't have a cylinder if we're at one of those two endpoints. We don't have a cylinder if r equals 0, so I'm definitely not looking at that. So I just want to check, is r equals 4/3? First of all, is it inside of our domain? And it is. And then I'm going to check using the second derivative test to see whether this would be concave up or concave down. So if I take that second derivative, and I'm going to go back to the not factored one so that I don't have to do product rule. I'm going to have 12 pi minus 18, I'll turn that into an 18 pi r. So for sure, when I plug in that 4/3, this whole thing is going to be negative. So v double prime of 4/3 is less than 0. So it's concave down. So we did have a max. Now I go back to check what I was asked to find. I was asked to find the dimensions. By the way, I could have written this to say find the volume of the largest cylinder, in which case I would want to take that radius that we found and plug it back into the volume equation. But because I asked for the dimensions, I'm going to say that the radius is 4/3. And for the height, I want to plug it back into our equation that says height equals. And that is hiding right down here. So I would say my height is 6 minus 3 times 4/3, or 2. We're measuring the distance between these two things. So that phrase closest to really means minimize the distance or shortest distance. Closest to means minimum distance. Oops, not mime, about minimum. Minimum distance. We're going to need that good old distance formula. So our distance between 2 points is the square root of like x2 minus x1 squared plus y2 minus y1 squared. There's a trick that our book uses when we're talking about minimizing distance. Our book actually tells us that we can minimize the square of the distance and have the same result. So we're going to minimize this instead. It's a trick in our textbook, and I feel like if it's in our textbook, it ought to be fair game for any quiz or test. So we're going to minimize this instead. We got to put stuff in that we know. So we know that one of our points is 0, 1. So I'll put in a 0 and a 1. And then essentially our other point is just some XY coordinate on this graph. So I could put this in as X and Y, but if it has to be on the graph, then I already know that Y is equal to X squared. And now you all know how to find a max or a min. Take a derivative, set it equal to 0. I will leave it up to you how you want to get through that derivative. This first piece, I don't actually need the -0, so I'm going to stop dragging it around with me. That piece is really just x squared. It's totally fine to write the -0, but I don't actually need it. So the derivative of x squared would be 2x. And I think that's going to help us out over here because when we do the chain rule, I think we're going to have a 2x pop out. So over here, I've got stuff squared. So I'd have 2 times that stuff to the first power, and then times a 2x from the inside because of chain rule. When I set that equal to 0, I can pull the 2x out from both, factor it out. From this first piece, if I factor out a 2x, I'm just left with a 1. And from this back part, I would be left with a 2 and then the x squared minus 1. So that's 2x. And then over here, I'm going to distribute the 2 in. So I'd have 1 plus 2x squared minus 2. Move that up just a little bit. Or 2x times 2x squared minus 1. Now, unlike the other problems that had some physical constraints, I would argue that we have no reason to believe that this has physical constraints. So I really should consider my entire domain to be the real number line. We're not like building a box or something out of this. So we don't really have constraints on the domain. Which means I have 3 values of x to consider. I've got that x could be equal to 0. And then from this one, if I come off to the side, that says 2x squared is equal to 1, or x squared is 1/2, or x is equal to plus or minus 1 over the square root of 2. So we can definitely use a sign chart here. Or we can do the second derivative. I don't have a particular preference. Other than by default, I usually end up doing the second derivative test. So if I'm going to do the second derivative test on this, I want to go back to that first derivative, which is right here, but I kind of don't want it in the factored form because I try to avoid product rule whenever I can. So if I distribute that out, that's 4x cubed minus 2x. So now I can take a second derivative and get 12x squared minus 2. And then check our points. So f double prime of 0 would be -2. F double prime of 1 over the square root of 2. So that's 12 times 1 over the square root of 2 whole thing squared minus 2. Well, when I square that, it's 1/2. 12 times 1/2 is 6. 6 minus 2, definitely greater than 0. And if I do this with a -1 over the square root of 2, I have basically the same result because when I square that negative, I also end up with a 1/2. And then times 12 is 6, and 6 minus 2, that's greater than 0. So both of these represent minimums. This one represented a maximum. So we're not going to use the x equals 0 value. Now I've got to go back to the question to make sure we answer the actual question that was written. And the question that was written was to find the points on the graph. Points mean I have to give an x value and a y value. So one of my points is a positive 1 over the square root of 2, comma. But when I plug that in here, I get 1/2. And negative 1 over the square root of 2, comma, 1/2. So those are my final answers. And they're 4 miles from the nearest point on a straight road. If you can walk at 4 miles per hour in the sand and 5 miles per hour on the road, find the shortest time it will take to walk into town that is 12 miles down the road from the point that is closest to her. Yay, good times. Just like that over there. Perfect. But, and then wait for everything to come back into focus. Dude, this is like, there you go, maybe. I definitely think this is a problem where I would like a picture. So we've got the desert out here. We've got a road. So here's the road. And we're trying to get to town over here. So here's town. And town is 12 miles from this point. And the hiker is currently out here in the desert. Four miles from that point. And basically the dilemma here is she can walk faster on the road than through the sand out here. But we all know the shortest, or you've probably heard the shortest distance between 2 points is a straight line. But that doesn't mean that it's her shortest time. So if it takes longer to walk through the sand, like if she walks slower through the sand than on the road, then there's some optimal place to target over here so that part of that time is spent on the sand and part of that time is spent on the road. And I don't know about you, but I believe that I have actually in my brain tried to work out this optimization problem a time or two when I was at the beach, because I really do hate walking on sand. And sometimes I'm like thinking about where should I walk to in the parking lot to avoid like walking the whole time on the sand. So not that everyone's had that experience, but I have definitely had that experience. So now we get to the tough part. Well, the question asked us to find the shortest time. And if what I'm looking for is the shortest time, I have to start by writing an equation for time. I'm just going to start in words. So I know that the total time is going to be her time in the sand plus the time on the road. And we were told something about the rates at which she walks, that 5 miles per hour and 4 miles per hour. So now I'm thinking, okay, let's go back to distance equals rate times time. So that time must be the distance divided by the rate. So I'm going to write this instead as the distance on the sand divided by the rate. in the sand plus the distance on the road divided by the rate for the road. Now it's time to get into our picture. Doesn't really matter how we work this, but let's call this part in the sand. I don't like to use S because my S's kind of look like 5s. So instead of calling it an S for sand, I'm going to call it a D for sand. I'm going to call D that distance in the sand. And the rate in the sand is 4. So if that's a D, we need an equation for the distance on the road. Does anyone have any brilliant inspiration for how we're going to come up with the distance on the road? Something minus 12. Yeah, for sure. Something minus 12 sounds good. So whatever this road piece is, it's that something minus 12. I'm just going to give that something a name. I'll give it B. So yeah, that distance on the road is definitely like 12 minus that little b that we cut off over 5. But then I'd look at that and go, oh darn, I have too many variables. I need to know something else. And that something else I'm going to know is that now I have a triangle that I can Pythagorean theoremify. So if I look at that triangle, now I've got that 4 squared plus b squared is equal to d squared. And I can get rid of that b because b squared would equal d squared minus 16. By the way, I don't have to worry about a plus or minus here. It wouldn't make any sense to walk totally away from town and then walk it back in towards town. So we're only going to take that positive value of b here, which means my time is going to look like d divided by 4 plus 12 minus the square root of d squared minus 16, whole thing over 5. Good times. Now I'm going to pause for just a second to say we do have real world constraints on D, right? So let's just name that in terms of our domain. I would say the two extremes here are either that I just walk straight across the sand, straight across that hypotenuse, or that I walk to that point and then across. And all the other paths are somewhere in between those two. So that value of D, that distance across the sand, the shortest amount that we would end up walking is 4. And the largest amount that we would end up walking is the hypotenuse of that like big triangle. So my domain is that D would be somewhere between 4 and the hypotenuse of that big triangle would be the square root of 4 squared plus 12 squared. Now, unlike the other times where we had this shape, and if we actually hit the extreme, we were going to not have that shape anymore. I am definitely going to include the endpoints on this one because it is totally possible to just walk those 4 miles straight or to walk that whole distance to town. So there's our domain. How are we feeling? You want to take that derivative on your own, or are we going to do it together? I'm going to give you some advice. I would definitely rewrite that before I choose to take a derivative. You don't have to, but I would choose to write that as 1/4 of d. Split this into 2 fractions. So plus 12/5 minus 1/5 of d squared minus 16 to the 1/2 power. That's the thing I personally would rather take a derivative of. And since I got a couple requests on Zoom to do this together, in the interest of time, let's go ahead and do this together. So when I take that derivative, I'm going to get 1/4 plus 0 minus that 1/2 will come down. So I'll have 1/5 times 1/2 and get 1/10 of d squared minus 16 to the negative 1/2 times 2d. And that whole thing has to be equal to 0. Now I know I've been factoring stuff, but I don't really know how to do this with factoring. So I'm just going to rewrite these pieces in as neat a form as I can. So the 1/4, there's not much I can do with that, but this whole thing, I've got like that 2d that's on top of the negative 1/10. And because that's to the negative 1/2, I can go ahead and put it back down here in the denominator. So if I add this to the other side, I'll have 1/4 is equal to 2d divided by the square, 10. You know what? Why don't we just reduce that 2 and that 10 and call that a 5? And say that that's d over 5 square root of d squared minus 16. And then I would multiply both sides by all the denominators and end up with 5 square roots of d squared minus 16 is equal to 4d. Grant wrote this problem and I'm really crossing my fingers right now that it works out nicely. So if I were going to solve that, I'm going to square both sides to get rid of that square root. So I would have 25 times d squared minus 16 is equal to 16d squared. Or 25d squared. I don't even know what 16 times 25 is, so I'm just going to leave it written like that. Is equal to 16d squared. So I can get all my d squareds on one side, and 25 minus 16 should be 9, right? 9d squared is equal to 16 times 25. Now, the reason that I left it like that is because I knew that nice things were going to happen in the end, and I knew I was going to end up taking the square root again anyway. And mostly I didn't want to multiply out 16 times 25. It's probably not that bad, but I'm going to do 2 steps at once here. I'm going to divide by 9 and also take the square root. So when I divide by 9, I'd have, well, okay, I won't do 2 steps. I'd have 16 times 25 all over 9. And then when I take the square root, because everything over here is multiplication and division, when I take the square root, I'm taking the square root of each thing. So that's 4 times 25 divided by 3. I mean, how about 4 times 5 divided by 3, or 20/3. I don't know exactly what the value of 20/3 is, but we can kind of fake it. 18/3. Oh, how about 21? 21/3 would be 7. So it's a little bit less than 7. So if we go back to our picture, we're saying that we're going to aim for this distance to be about 7, and then we'll walk the rest of the way on the road. Which begs the question, is it within our domain? And I'm going to say, yeah, it probably is. But let's give ourselves a reality check. So 4 is less than or equal to D is less than or equal to 4 squared is 16. 12 squared is 144. 16 and 144 sounds like the square root of 160. Did I do that right? I don't know what the square root of 160 is, but I know that the square root of 169 is 13. So that's probably just a little bit less than 13. So 7 is definitely, 7-ish is definitely between 4 and 13. So we're good, we're in the domain. Oh, thank you, someone threw it in a calculator. This is about 12.64, thanks. So we still need to check, was that really, and this time we're looking for the shortest time. So we're hoping that that results in a minimum. This might be one where I'm going to look at that and say, the second derivative doesn't look great. Maybe we should just do a number line this time. So if I were to think about a number line or that T prime, our world starts at 4 and ends at the square root of 160, which we know to be approximately 12.64. And this number that we've got going on is 20/3. So I'm going to pick something in here like 5. I'm going to pick something over here like 10. And I'm going to plug those numbers into my first derivative to figure out if it's positive or negative. I'm going to go with this version. So if I plug in 5, I'd have a 10 on top and a 10 on the bottom. So those would cancel out. 5 squared is 25. 25 minus 16 is 9. So I'd have 1/4 minus 1/3. That's negative. We're going down. If I plug in 10, oh, I wrote X, but really our letter was D. So I'll be a little more careful about that. So if I plug in 10, then up top, I've got 20 over 10. So that's 2. 10 squared is 100. 100 minus 16 is 84. Oh man, so I've got 1/4. Maybe I should have picked a different number, but I've got 1/4 minus 2 divided by the square root of 84. Well, for sure that's positive. Why do I know it's positive? Because I know that 2/8 is what would equal 1/4. And whatever the square root of 84 is, it's bigger than 8. By the way, I recognize that most of you probably have a calculator right in front of you. I'm just trying to talk through how I would figure out those numbers if I didn't have a calculator. For sure on your homework, if you're working through web work, just pull out a calculator and figure out what that is. But if you don't have a calculator in front of you, that's kind of the process I would talk through. So it is in fact a minimum. Woohoo! So now we go back up, read the question again to see what the heck they were looking for. We want to know, find the shortest time. So the question has asked us for the shortest time, which means we're not done. Our final answer needs to be what the time equals. So we know that D is 20/3. And we are looking for the time at 20/3. And again, if I don't have a calculator, I probably am not going to try to simplify that. I'm just going to leave my time as saying 1/4 of 20/3 plus 12/5 minus 1/5 of 20/3 squared minus 16, all to the 1/2 power, and call it a day. Whatever that equals. In our remaining 6 minutes, shall we try to get through a curve sketching problem? Or should we say, that's a lot of math for one day. I'm seeing some head nods. Let's say that was a lot of math for one day. Let's just be done. Let's be proud of ourselves for doing all of that in one day. Yay, go us. I know that was a lot in terms of this problem. I don't know if anyone had questions about this one. I'm not seeing questions in the chat. So that is a good question. Are problems like the one we just did common on a test? No. I would say problems like this definitely show up on homework, for sure show up on the web work, but problems like this don't typically show up on a test. And I would say they don't show up for 2 reasons. From a really practical standpoint, I don't want to grade this. There are just too many places where a small mistake is going to lead you down a bad path. And so from a really practical standpoint, instructors like to write test questions where really there's probably only one process you're going to choose to use to answer it. I will say all of the other questions we did today are typical test questions, including the shortest distance between a point and a curve. That's a common test question. Things where we're inscribing under a shape or inside of an object. Those are all very typical test questions for optimization. The other super typical test question is something like we did last week, where you have a fixed volume and you're trying to minimize the surface area. That's another super common one. But something like this is more in the realm of homework and web work stuff. We'll have a level, I know y'all have class tomorrow unless your instructors have canceled class, but have a nice break. And I will see you all in a week.